now I will start the third lecture of week 11. In the last lecture, we learnt about Bloch's theorem and how Bloch's theorem can be used to describe electrons in a typical solid, and we qualitatively saw how bands how we can roughly understand what bands are. So, in today's lecture I will be talking about the band theory of solids, and we will go into slightly more details and we will try to do it a little bit more formally. Okay. We still will not be able to do it in very accurately because the problem is not solvable exactly, but we will be able to see how bands appear. Okay. So, today's lecture will be on band theory of solids. So, let us we will talk about the system of non-interacting electrons in a lattice. So, what I mean is that you have a solid, okay, and you have all these ions. Okay, I am just showing them as black dots here. Okay, and you have a lattice of ions, and in this lattice you have electrons which are essentially, except for the lattice, they are just moving freely. Okay. And we want to think about how what this will look like. Okay. Okay, we want to think about what this will look like, and what we said, okay, is that according to Bloch's theorem, the presence of a lattice implies that these electrons can be described individually by a wave function, okay, that has the following form. So, psi n k of r, this is equal to e to the I k dot r times u n k of r. So, this is Bloch's theorem. Okay, and I am not going to prove this. Okay, you can look up standard reference standard texts for the proof, but that is not important. What Bloch's theorem also says is that you can write the wave function of these electrons moving in a lattice by this, okay, where u n k of r is equal to u n k of r plus some vector belonging to the Bravais lattice. Okay, R is some vector belonging to the Bravais lattice. So, this is a lattice translation vector. Okay, so, R could be any of these vectors. So, you could have R like this, any of these could be R. Okay, you could have R is one of the lattice translation vectors. Okay. And what Bloch's theorem says that you can take any lattice translation vector, okay, and add it, and since this u n k which appears in the solution of the wave function is a periodic function. So, you have a periodic function multiplied by e to the I k dot r. Okay. Now, let us ask, we are going to write this in an alternate form. So, alternate form of Bloch's equation, which is actually very useful and very incisive. Okay. Now, let us ask the question, what is psi n k of r plus r? So, suppose I ask what is this? Okay. So, now if I do the same on the right hand side of the wave function, okay, then you will get e to the I k dot r plus r times u n k of r plus r. Okay. Now we know that u n k of r plus r is just u n k of r. Okay, and I will write this in the following way. I will write it as e to the I k dot r multiplied by, what I will have is e to the I k dot small r, and since u n k of r plus r is same as u n k of r, I will just write this as u n k of r. Okay. So this is written as e to the I k dot r times psi n k of r. So this is what we had here was just psi n k of r. So we have this alternate form of Bloch's wave function, alternate form of Bloch's theorem, okay, is that your wave function can be written in this form. Okay. So whether you write it whether you write Bloch's theorem in this form or this form, it is actually the same. Okay. Now there is something that something nice that happens when you write it in this form. Okay, that is the following. Suppose you ask the question, what is psi n k plus capital K of r? So let me ask the question, what is psi n k plus capital K of r plus r? Okay. So now from this form of Bloch's theorem, okay, this can be written as e to the I k plus capital K dot r times psi n k plus capital K of r. Okay. Now we have a very nice theorem, okay, that states that e to the I capital K. So capital K. Now what I mean by capital K is that capital K is it belongs to the reciprocal lattice. So the reciprocal lattice that we talked about earlier. So K is a vector of the reciprocal lattice, okay. And now what this says is that since it is a vector of the reciprocal lattice, you have e to the I, a vector of the reciprocal lattice dotted into vector of the normal lattice should be equal to 1, okay. And so if you expand this and you take it to the next step, you will see that this has an implication that psi n k plus capital K of r is equal to psi n k of r. Okay, I am not showing the intermediate steps, but you can use this, okay, and you can manipulate this to show this final result. Okay, and the other relation that we get is that E, the energy of the Bloch electron, epsilon n k plus capital K is equal to epsilon n k. Okay. So these two equations here, they describe the periodicity in reciprocal space. Okay. And this is a consequence of Bloch's theorem, okay, that your wave functions are periodic not only in real space, but they are also periodic in reciprocal space. Okay. And again, let me emphasize that I have not shown all the steps going from here to here, but you can work it out. Okay. Now what else do we want to say? So now let us use these ideas in looking at electrons on a one dimensional lattice. Okay. Now if you have only one dimension, okay, so in one dimension there is only one Bravais lattice, and this lattice is you can think of it as just we can take atoms on a line equally separated by distance a. Okay, so they are equally spaced by distance a, and if you have all these ions, and now you have this electrons that are going in this. Okay, so this will be a very nice illustration. We will see how bands naturally appear. Okay, now these electrons, okay, they are like so except for the ions, the electrons are just moving freely. So there are ions, okay, which impose a periodicity. So let us look at free, okay, and I am putting free in quotes because these are free electrons on a lattice. Okay, and in what sense do we mean that they are free? That means in between there is no interaction potential. Okay, they do not feel any forces in between, but there is a periodicity up that is imposed on the wave function. Okay, so what we have is that we have epsilon k. So for a given wave vector k, the free particle solution, say that this is h cross square k square, in this case this k is just a scalar, h cross square k square by 2 m e, the mass of the electron. Okay. Now, so on this lattice, these electrons are not really free. There are some periodic, there is a periodicity of the lattice. But now let us just look at this. Let us look at this relation. So I will put epsilon as a function of k. Okay, and let me do this in the following way. I will choose okay. Now notice that in the reciprocal lattice, okay, so that looks like it is equally spaced points in k space. Okay, so this is in k space, in wave vector space, but the spacing between the points is actually 2 pi by a. Okay. Now, in other words, what we are going to say is that this energy of k is equal to energy of k plus 2 pi by a. And basically it is 2 pi by a times any integer, Okay, so it can be plus 2 pi by a, it can be minus 2 pi by a, plus 2 into 2 pi by a, minus 2 into 2 pi by a, and so on. Okay. So what we are saying, let me extend this graph a little bit on this side, okay, just to illustrate the point that that if you look at this energy versus wave vector, okay, you will get some relation that looks like so it looks like this. Okay, so this is just a it's a parabolic function. E k is h cross square k square by 2 m e. So it is just a parabolic function, and it look like this. Okay. Now, since you have this Bloch condition, okay, what you will get is you will get another parabola in energy. So, this is 2 pi by a, and here I have another parabola that looks exactly like this. So, since the wave function here should look exactly like since this wave function should look exactly the same at 2 pi by a. Okay. So, at 2 pi by a, just due to periodicity, I will have exactly the same form of the wave. And it will go out. Okay. And they will cross each other exactly at pi by a. So, I have to draw this properly. They will cross each other exactly at pi by a. Okay. So, now we will have similarly we will have something coming from the other side that will also look like this. Okay. That is coming from the left, from minus 2 pi by a. This is minus 2 pi by a. Okay. And so you have this form of the wave function. Now, since the energy is a periodic function, okay, you only need to describe the energy in this interval. Okay, and notice we have just used the free particle form of the energy. So, this energy form that we have used is actually, it actually corresponds to the free particle. Okay. Now, if you just look in this region, okay, then you see what the energy looks like. Okay, and let me show it in a different color. So, it looks like this. Okay, and then there is another band that looks like this, and a third band that looks like this. Okay. So, you can, let me show the bands in different colors again, just to. So, you can see that just due to periodicity, you see this kind of bands forming. Okay. So, again let me emphasize that we have used free electron form of energy. So, free electron form of energy used. Okay. And the other point I want to emphasize is that though we show these k as a continuous variable, it is actually discrete variables. Okay. This is due to the von Karman boundary condition. So, actually there are only discrete values of k, okay, but they are very closely spaced. So, it looks like a continuous set of values of k. Okay. So, again just using the free electron picture, okay, and we are just so the role of the lattice is just to bring this periodicity, okay, and we see that if you look in this region, then we see a band like picture appearing. Now, incidentally, this region from here to here, this region, okay, this region of k from minus pi by a to plus pi by a is called the first Brevard zone. Okay, this is in 1D, the first Brevard zone just looks like a region in k. minus pi by a to plus pi by a. So, if you know the energy in the first Brevon zone, you can actually calculate the energy everywhere else, okay, just by imposing the periodicity of this first Brevon zone. Okay. And I should also emphasize again that there will be more, I mean I have shown only some of the periodic some of the parabolas, but there will be also be more parabolas, okay, and that will there will be, for example, there will be another parabola that that passes through this, that starts at 4 pi by a and it goes like this. Okay. And so, essentially what I want to say is that this whole thing will just keep repeating. So, you will see that again you will have exactly the same kind of behavior in each of the zones, each of the Brevon zone. Okay. So, even in this zone it will be exactly the same. Okay. Now, with this basic framework, okay, we can go to the, so here the free electron form of the energy is used, okay, and so the lattice actually causes a very little, the ions do not perturb the electronic wave function. Okay. So, in this form, in this description, the ions do not, it is as though the ions are not perturbing the wave function, but now we can take this and we can add the idea of perturbation. Okay. And so if we think that the ions that are there, they will actually add a weak perturbation, okay, then what you can say is the following. So, what you can say is that this weak perturbation will actually change the band structure right where these lines cross each other. Okay. So, like this region, etc., there will be some perturbation. Okay. We will see that in a few minutes. Okay. Now, let me, so based on this depiction of bands, okay, you can, there are a few different ways to represent bands. Okay. Now, one is called a repeated zone representation, where you show all the zones, okay, where all the zones are shown. So, for example, if you have the first Brevon zone, the second Brevon zone, and so on. Now, then what the idea is that you show all the zones, you do not only show in the first zone. Okay. So, your in the first zone, if you have something like this, and a similar thing on this, again I am considering the free particle form of the functions. Now, in the second zone, you will have a similar thing. Okay. You will have something like this. Similarly, in this zone also you will have something like this. Okay. This is called a repeated zone representation, where you show all the zones. Okay. So, all zones are shown. Okay, so this is called a repeated zone representation of the bands, and again let me emphasize that here I have considered non-interacting or free electrons. Okay, but you can do this for arbitrary bands. Okay, so for arbitrary bands in arbitrary dimensions you can do this. Okay, by A minus pi by A minus 3 pi by A. The alternative to this repeated zone representation is the reduced zone representation, where you essentially focus on one zone and you show the band in that zone, and we already saw what this looked like. Okay, I will just show this again. So, you just show the first Brevard zone, which is minus pi by A to pi by A, and if you look at the bands, okay, they will go like this, and then they will go like this, and so on. And you will have more bands. Okay, you will also have bands due to things that are even further away. So, you will see you will have things like this. Well, okay. So, I am showing here I just showed the first two bands, okay, and or the first two just due to this blue curve and this green curve. Okay, but you could have more band structure, okay, due to another band that is centered here, okay, and it will again go, and eventually it will come into the first Brevard zone. Okay, so you will also have more bands, and okay, and so in general in the repeated zone you will have several bands. Okay, and this repeated zones representation is also often used to describe bands. Okay, so you can either or the reduced zone. Reduced zone means only first Brevard zone. Okay. Now let us ask the question, what happens if there is a small interaction, if there is a weak interaction in this band structure. Okay, so what happens to the band structure if there is a weak interaction, and formally this is done using nearly free electrons. It is a perturbative approach. Okay, so the ions cause a small perturbation to free electrons. Okay, so the Hamiltonian, okay, is the Hamiltonian of the free electrons plus some small perturbation. I will just write delta u. This is a perturbation. Okay, and without going into too many details, okay, you can understand this in a very similar way to how you understand orbital theory, molecular orbital theory. Okay, the basic idea is that if this perturbation is very small, okay, it will only affect, so the solutions okay will look like the energy is equal to energy of free electron, okay, plus something that is related to delta u times I'll just write some function of delta u. Okay. Now, what is important in this perturbative approach is that this function, okay, will only be non-zero when energy levels cross. Okay, and I again I'll just show this qualitatively. Okay, so if you go back, let's look in the repeated zones representation. So we had a wave function that looked like this. Okay, and you had a second wave function that is, let us say, starting here, that looks just like this, but shifted by 2 pi by a. This is k energy, and you have a similar one on this side also. So now what I want to say is the following, that right at these points where the energy levels cross, okay, this is where the perturbation will be active. Okay, and what the perturbation will do, okay, it will do something that should be very familiar to you. Okay, you might have seen this in energy levels of molecules. Okay. So, what it will do is that the perturbed energy, and let me show this in light green. Okay. So, it will look very much like the free electron, okay, except close to here it will move away. Okay. So, in some sense these two energy levels will repel each other, and one will be pushed down, the other, which I will show in a different color, okay, will be pushed up. Okay. The same thing is going to happen here too. Same thing is going to happen here. Okay. So this energy level will be pushed down here, and it will become like this. Okay. And whereas this energy level will not be perturbed far away from the intersection point, but right near the intersection point it will be pushed like this. Okay. So our final band structure will now look like this. So let me erase this. It will look erase this too, look like this. Okay. So that is what the band structure will look like, and if you look in the reduced zone, if you just look within the first Bremont zone, okay, then what you see is you see a band. Okay, let's go to the lowest band. So you see a band of energies. So this is a band of energies from here to here. Okay. And then you see something here which is caused due to the perturbation, that is this is called a band gap. and what has happened is that because these because of this perturbation, and then you have another band of energies from here to here. Okay. Okay. And again you have a band gap, again you have a band gap here. And then you have another band of energies here. Okay, these are continuous. Okay. And the point is that this explains the origin of band gap. Okay. So, this nearly free electrons, a perturbative approach explains origin of band gap. Okay. How band gap appears. Okay. And notice that we have just used the free electron, one dimensional free electron picture. Okay. And just putting this perturbation, and I have not done the mathematics of the perturbation, but I have just qualitatively told you that this perturbation leads to a band gap. And so now if you look at just in the first Brillouin zone, okay, then you will have and what we had was something like this, and then something like this, and again you will get something like this. Okay, if you extend the bands, you will keep getting things like this. You will keep getting this alternation of bands that are either going either like this blue, which going from 0 to pi by a, it goes down or it goes up. Okay. And you will see this band gap in several places. Okay. So, so we see that this nearly free electron model, okay, which is basically a free electron with this small perturbation, okay, that gives a nice band structure in 1D. Okay. So we have both the origin of bands and the origin of the band gap seen in this. So, with this I will conclude this lecture. In this lecture we have seen how you can understand the origin of bands and band gap in 1 dimensions. Okay. Now, in 2 dimensions things become a little more complicated in 2 and 3 dimensions. Okay. But so in the next lecture I will just briefly show you what happens in 2 and 3 dimensions, and we will come to the concept of a path in reciprocal space. Thank you.